Hello, my name is Todd Rothman, and I want to welcome you back to Organic Chemistry 1. In this video, we're going to go over quantum mechanics. Now, quantum mechanics is probably one of the first areas in organic chemistry where students have a lot of difficulty. And there's really two reasons for this. The first one has to do with the fact that quantum mechanics is a very difficult field. It's a very challenging field. There's a lot of math in quantum mechanics, which we really aren't going to be exposed to. But that leads me to the second point. The reason why this is challenging for students is because quantum mechanics is an entire field. It's actually one of the hottest fields. It's got a lot of inspiration, a lot of research going on, a lot of people finding new things from quantum mechanics. But the thing about it is, from our point of view, we just have to go on the outer skirts of its points. So we don't really need to go into every level of detail. We're not going to learn the formulas. We're not going to prove how the things that we get from quantum mechanics is true. We just are going to take it for face value. Now, even if you were a physicist studying quantum or doing research in quantum mechanics, there's a lot of things that are really weird that comes out of it. A lot of wild points and a lot of very deep thinking. So even they have a hard time with quantum mechanics. So we, of course, do as well as organic chemists, because we don't even get to know all the details. We just have to kind of take things for face value. Now, this is a challenge for a tutor and for you. And what I like to do is I like to build a story. So I'm going to go through quantum mechanics by teaching you things. Some of it is more of just for story building, and other parts are things you have to know. And I'll emphasize which one's which. Okay, so you'll kind of get the points. We're going to lead up to the real meat and potatoes of what you need to know. Okay, but we're going to build our way up to it, and you'll appreciate this because you have to know quantum mechanics and the orbitals and things relate to antibonding and bonding for the whole year. And so a lot of times people just look past it and they don't really dig into it as much as they should. And then throughout the semester, it keeps popping its head up. All these little principles of quantum mechanics comes up, and then you have to relearn things or you find yourself confused. And in particular, I'm thinking about when we learn about antibonding and bonding and the different orbitals. Okay, so it's really an abstract science. This whole quantum mechanics is very abstract. I find it personally to be very interesting, but it's very challenging to learn. Okay, so we're going to see that together we're going to go through this and we're going to build a really good foundation for the rest of our semester in Organic Chem 1 and 2. Okay, but let me emphasize one more time. Don't just look past this subject and try to create quick ways of learning it or ignoring a lot of the meat and potatoes, because there are things in here that you will need to know for the whole year. Okay, so give yourself the time to learn this. Okay, now here's how we're going to break this up. I have 9 topics that we're going to cover. The first one is a traditional way of starting, because this is kind of where it all began, and that is with the Bohr Model. The Bohr Model has some really interesting points in it, but a lot of things about the Bohr Model just don't work, and that's what number 2 is about. We're going to kind of see where the problems are in the Bohr Model and what kind of triggered or inspired people to go in the direction of quantum mechanics. Okay, so that's what we're going to see. We'll learn about de Broglie's contribution, the Heisenberg uncertainty principle, the Schrodinger equation, which we're not going to see the equation. We're going to understand what the results are from this equation. We'll talk about standing waves because that's critical for your understanding of orbitals. We'll learn about how to combine standing waves, and then we'll take that to the orbital point of view. We'll learn about combining orbitals. We'll learn about sigma and pi bonds. When we're done with this video, you'll have a very good understanding and a great foundation to build your knowledge from. Okay? Just give yourself the time and make sure you follow this carefully. All right. And again, remember, I'm going to build a story, so some of it you don't need to know. It's just for story building purposes. But you'll get what you need to know from this. The next video is going to be about hybridization. So we're going to take our fundamentals from quantum mechanics and we're going to apply it to hybridization in the next video. Okay? So let's get started. The first place to start is, what is quantum mechanics? Now, we're going to jump the story a little bit, and I'm going to say here that electrons have wave and particle properties. This is the basis. This is what inspired this field of quantum mechanics. So all of a sudden, after this was discovered, which we'll talk about in a moment, this idea, we had an influx of people doing research and proving and challenging. There's a whole bunch of cool stories about this with Einstein and Heisenberg. There's just such cool stories of people that were involved in this when this came about. Now, quantum mechanics is a mathematical explanation of that characteristic, that dual characteristic. The fact that electrons have this both a wave and a particle property to it. Now, it's also about the energy associated with that. So we learn a little bit about energy and how electrons and how energy influences these electrons, such as photons or just electromagnetic radiation in general. Okay, and so it's an interesting other point is to see how energy influences these electrons. Now let me say one last thing and then we'll get started with the story. And that is that with quantum mechanics, it really is an interesting science because it's something that's every year there's new things coming out of it. So it's still it's very early. It's a very young science, okay, or field of study. And so there's a lot of cool discoveries coming out of it all the time. All right. Anyway, let's go back into this foundation. So we start with the Bohr model, and we all kind of know what the Bohr model is. We've been describing it in Gen Chem, and we've talked about it even in our previous videos in this course. So let's talk about it now a little bit more organized. Now the Bohr model is kind of like a planetary model. Now what that means is Bohr's idea was that electrons are going to somehow orbit around the nucleus. So they kind of travel around the nucleus and almost like a planetary model, right? Like how the sun and the earth and the moon. And so the idea is an orbiting model. And now here are some of the key points that came out of this. So number one, electrons are going to travel in a circular orbit. And like I just described, the energy of the electron is directly proportional to the distance. And this we kind of understand already, right? Because we talked about how if you're further away, there's a weaker attraction, closer, stronger attraction. So the energy, of course, is proportional. And that's the other point that he made here. Now, this is something that's very powerful, this next statement, and that is that the energy is quantized. Now, what does that actually mean? So from an electron point of view, I wrote it here. It means that there's a discrete distance from the nucleus. So electrons aren't just randomly moving anywhere that they feel. They are at specific locations, discrete positions around that nucleus. Okay, now think about quantized. That's a very interesting concept. Quantized means that you have these clear levels. For example, I'll give you a good example. Let's say I'm running and I start at 0 miles per hour and I want to get to, I don't know, 1 mile per hour. Okay. Now, when I do that, if I'm not in a quantized state, if it's progressive, then I will go from 0 and I'll build my way up until I get to 1 mile per hour. But imagine if I'm running and there is no in between. So I start at 0 and then from that, boom, I just go right to 1 mile per hour. And then boom, I go to 2 miles per hour. See, nothing in between. I'm not going 1 mile and then 1.1 mile, 1.2. It's just from 1 mile to 2 mile. There's nothing in between. That is called quantization, where there are only certain levels and there's no building up to that level. That's it. It's just here and here and here and nothing in between. Very powerful concept, okay? That's what it means to be quantized. Now, electrons have, and by the way, so electrons have this. They have these clear positions, and they don't just move to the next position. They literally just appear at that next position. So they kind of are here, and then they're here. But there's nothing in between. Kind of crazy, actually. Anyway, electrons have a fixed angular momentum. Okay, so that I think is kind of clear. And so it has to have a certain momentum, but it's not changing in momentum. It's fixed. A photon with the exact energy difference between the energy levels can promote it. Now, this is the thing. When you're at one energy level and then the electron goes to the next one, like I said, it's quantized, so there's no in between. So when you give it a photon, which is going to allow it to go to another level, if it's the right energy amount, the photon, then it just appears at this next level. And then that's it. There's nothing in between. It doesn't climb to the next level. It doesn't build up. It just is here. And then if it's enough energy, boom, it's at the next level. That's what.